Okay, so when it comes to naming sugars and disaccharides, we have a couple of simple rules that we follow. And this is just kind of the steps to go through that so you get all the pieces in your name. And this is how I just found it was easiest to go through it. And so our first step is going to be, is it alpha or beta? And we know birds fly, so beta is going to point up from the ring structure, and alpha is the symbol in there, or fish swim. And so fish swim in the ocean, it's going to point down. And so if we look at our first structure here, this one is glucose. This would be that carbon that we're looking at, and that OH group is pointing down. Fish swim, so this would be alpha. Our second step is going to be to determine if it's D or L. So we look at the last CH2OH group and determine if it's above or below the ring. If it's D, it's above the ring, and most sugars in nature are going to be D. So you go back to our glucose example here, it is above the ring, so it's going to be D. The next question is it aldo or keto? Aldo is at, meaning like in the ring structure, is there one CH2OH group? Keto is if it's two. You're not going to see three, that would be a fake sugar, in her words anyway. So over here we have one CH2OH group, so it's aldo. 4, pento or hexo. So this one we are counting the total carbons. This is different than step 5. So when we are counting our total carbons, she says pento or hexo because we're going to have most sugars are going to be, all sugars fall within the range of 3 to 7 carbons. Pento means 5 carbons, hexo means 6 carbons. So when we come over here, we're going to count it up. And so here's our first carbon, 1, 2, 3, 4, 5, and then our 6th one is up here. So that one would be hexose. Our next step is going to be determining the ring style. So this is where you get into like furanose versus pyranose and where things get confusing. The biggest thing to know when it comes to the ring style, furanose is a 5-membered ring. Does not mean 5 carbons total like it does up here. 5 members in the ring. Pyranose is 6 members in the ring. Again, this is different than hexose. So, if we count the things in our ring, we're going to find that we come up with 1, because we have to count the oxygen. It's part of the ring. 2, 3, 4, 5, 6. Keep going in our ring. This is 1 again. We always count clockwise, and that's just standard for all ring structures. Our 6th step is to determine this anomeric carbon, and this will also play into whether or not we have like a sugar residue on the end. And so the anomeric carbon is going to be the carbon with the double bond when we draw it in our Fisher projection or that linear one. Usually it's going to be right next to the oxygen in the ring structure. So, in all of the examples that she has given us, if we go one right next to our oxygen, this right here would be our anomeric carbon. That is because this OH group was the last one to form, which means it's the first one to break off. And so our sugars flip from being a ring to being that straight Fisher projection. And so this end will open up, flip, rebond, and then do its thing, come back, open up, and then flip back the other way. So it switches between alpha and beta, and so at any point it's 50% alpha, 50% beta. That's why we care about the alpha or beta to begin with. So that is just naming individual sugars. So if we run back through this, glucose here is going to be an alpha because that group is pointing down. It's going to be D because the CH2OH group is above the ring. It's going to be aldo because we only have one of those groups. It's going to be hexo because we have 6 carbons, numbered in orange, on here. It's going to be a pyranose because we have 6 things in our ring, and we count the oxygen because it's part of the ring. And then our anomeric carbon is going to be this one that's circled. That's glucose. Where things can get funny now is when we start drawing in bonds. And so, if we were to take and make the official bond here, We know that this is actually an OH, but carb scientists are weird and they want to be special. So that is going to bond with this OH group down here. And so we would make our theoretical bond here, and we'd end up with H2O on the other side. That's more organic chemistry than you need to know. We just know that this goes away, that goes away, and we move this oxygen into a bond right here. Ta-da! So, looking at this sugar, you can go ahead and try and name it on your own, going through our 6 steps here. But at the end of our 6 steps, we'll find that our anomeric carbon is going to be the one right next to our oxygen. And normally that one can flip on its own, but now it's stuck in a bond. And this one is stuck in a bond. So they can't flip anymore, which means they can't be sugar residues anymore, because in order to do that, they have to be able to flip back and forth. And so we have formed an alpha-alpha bond, right? I'll double check that for you. But we form a bond here that traps it into its current position, and so it can't flip anymore, which means it can't be a residual sugar or a sugar residue. This is sucrose as a structure. It's the only one that you're going to see that's written with glucose on top and fructose on the bottom. And it's the only one that does not have a sugar residue.